So it's my pleasure to introduce Viveka Erlandson from Bristol University. This is the second mini course, the first lecture of this second mini course. She will talk about hyperbolic surfaces and Mirzakhani counting curve.
Thank you very much, and thank you very much for the invitation to give this mini course. It's great to be here. Yeah, so I'm going to talk about Mirzakhani's curve counting, and I'm going to find what this means soon. But the goal is going to be to count certain closed geodesics on hyperbolic surfaces. And with certain, so I'm going to count certain subsets. And for those of you that saw my talk on Friday, it's actually, it sounds very similar, and the setup is similar or the same, but the kind of geodesic we're going to count is actually, well, they're different subset, but more than that, it's very different methods involved. So it actually, even if the beginning might sound very similar, it will be something different. So when I say certain closed geodesics, so in particular, for example, we're going to count those that are simple. So I'm going to explain soon what even I mean by counting geodesics, but if you understand what I mean, with certain, you could, for example, think about the subset of those closed geodesics that have no self-intersection on a surface, or more generally of a fixed topological type. Again, I'm going to define all of this soon. Technically, what I mean by fixed topological type, you take any closed geodesic you want and then look in its mapping class group orbit and look inside those. And I say hyperbolic surfaces, and in general, or often, we will consider hyperbolic structures on surfaces, but it's actually not necessary for what we're going to do. So it's going to be, we're going to be able to do this much more generally. Essentially, any nice metric you can put in your surface, the results are going to hold for, in particular, negatively curved Riemannian metric, but even the negative curvature can even be loosened. But you can also have more combinatorial or algebraic lengths that we will talk about. And in those cases, closed geodesics, instead, I will think about free homotopy classes of curves. That's why I really say counting curves instead of geodesics. So really, I'm not a dynamicist, so I do geometry. So my kind of goal of these lectures are not so much to get to a specific end. I mean, I would like to say something about, well, I'm going to state the theorem already today, and in the end, I hope to say something about the proof. But it's more important that I go over some of these tools that I'm going to use, some of these spaces I'm going to introduce. So it's more important for me that you learn something than we get to specific goals. So please stop me anytime you have questions. I'm happy to slow down. And yeah, I don't have a fixed goal I have to get to, so we can take it a bit easy. But yeah, so just a little bit of an outline of what we're going to do. So today I kind of just want to introduce these objects and give some motivation and state the theorem. Then about the next two lectures, we're going to talk about the space of measured laminations on a surface. I'm going to introduce train tracks, which is a combinatorial tool or to deal with closed geodesics or free homotopy classes of curves, but also deal with measured laminations. And the goal of that is to define a natural measure on the space of measured laminations called the Thurston measure. So this space of measured laminations can be seen as, in a certain sense, the closure of all simple curves, if you at least you allow weights on your surface. And the generalizations of that is what's called geodesic currents. Which can be viewed as so if measured laminations is somehow generalization of simple closed geodesics, the space of geodesic currents can be viewed as a generalization of all geodesics, so not necessarily simple. And then on Friday, I hope to say, return back to Mirzakhani's curve counting theorem. And either, depending on how much time we have, give an idea of the proof or give some applications to it. Okay, so that's a broad outline of what I'm going to do. But for now, let's just define the setting we're in and state the curve counting theorem. So throughout the talk, S, or the course, is going to be a topological surface. Always going to assume it's connected, oriented, or orientable. And this is actually very important for the theorem. The theorem fails for non-orientable surfaces. And finite type. Finite type, I mean the genus is finite, or number of punctures if we have any finite. So I want G is going to be the genus, and R is going to be number of punctures. And for most of the course, the number of punctures is going to be 0. I'm going to consider closed surfaces, even though the theorem does hold for puncture surfaces. Certain things are easier if we assume it's closed, but I don't want to do it from the very beginning, because the only place where I can draw pictures is in the puncture torus, so I want to allow punctures just for that example. And I want the Euler characteristic to be negative. So the smallest complexity surfaces are the once puncture torus, which we're going to talk about a lot, especially today, or the 3-hole sphere. But actually, I want to exclude, so I mean puncture or boundary, I'm going to use interchangeably. I don't want this. And the reason is simply if we want to talk about simple closed curves on this pair of pans, it's really only the ones that are the boundary components. So basically, it's not interesting in that example. So we're just going to exclude that. But any other topological surface or negative Euler characteristic is OK. Yes?
The punctures, they can be like cusps.
Yes, so exactly. So the punctured, so this is like this our smallest surface in a way. It's a torus with 1 point removed. And, or if you want, I think of the topologically, this is the same as putting a boundary component. But if I put the hyperbolic metric on this, yeah, then I'm going to want it to be a complete finite area surface. So then geometrically, it looks like this is a cusp. So geometrically, it's this. Yeah. Yeah. So first, if we just talk about simple closed geodesics, there's only 3. I mean, up to put weights on them. Right? There's no other simple closed geodesic here. I also want to talk about mapping class group orbits, and the mapping class group here is trivial or finite, depending on if you want to fix the boundary or not. Okay. So it's not a real, there's no technical, it's not an interesting example. But yeah, so just like you said, we're going to also want to put metrics on this, so natural metric, and why we have this is equivalent to saying S admits hyperbolic structures, hyperbolic metrics. That's why we have that condition of negative Euler characteristic. So S is topological surface. X is going to denote the hyperbolic surface, at least today, homeomorphic to S. Or equivalently, you have S and you put, sorry, maybe I should get some picture of my S. And possibly some punctures. So really you have a compact surface possibly with some finite set of points deleted from it. And as long as the Euler characteristic is negative, you can put the hyperbolic structure on it. In fact, there's infinitely many that you can put on the same topological surface. And so Andrea gave a very nice pre-mini course talking about a hyperbolic plane, hyperbolic surfaces. I don't know if it's something that everyone has seen, but many ways to think about hyperbolic surface. So it's a Riemannian metric of constant negative curvature put on it. We can also think about it, so the universal cover is isometric to H2. Pi1 of the surface, pi1 of X or S, whichever you want, can be identified with a discrete subgroup of isometries. I guess orientation preserving isometries. So discrete and free, so I have no fixed points of that. And then you can view the surface as the quotient space. Or more geometric, or it's the same thing. If you have a discrete subgroup of isometry groups acting on H2, it has a fundamental domain. And you can think of this as, so maybe some hyperbolic polygon with side pairing identified. So just like usually maybe used to seeing the torus, which is Euclidean, but a square with opposite sides identified, and you get the torus. You can do this more generally in a hyperbolic space. So maybe just you glue sides pairwise. And as long as, so this is Poincaré polygon theorem, as long as these satisfy certain angle conditions, you will get a hyperbolic surface out of it. But in fact, so I said that the things I'm going to say turns out to hold much more generally. If you want, so in this case it's an octagon, but in general take a 4G-gon, what you're going to get, so in this case it's a genus 2, you're going to get the surface of genus G, closed surface genus G. So maybe I should give some notation. Maybe I call this surface SG or. But yeah, so what I was going to say, even if we don't care about hyperbolic geometry, you could just take any octagon, say a Euclidean octagon, and just do this. Just glue it like this. What's going to happen is you're not going to get a nice manifold. You're not going to get a nice surface because you're going to get axis angle around the vertices. In this case, if we glue it like this, all the vertices are going to get identified. So you're going to get one cone point with too much angle. But that's fine. It's going to be Euclidean cone surface. So away from that cone point, everything looks flat, like Euclidean space. And at the cone point, all the negative curvature is going to be concentrated. So it turns out that this counting theorem up to constant is going to hold also for that metric. So basically, you can think of this very topologically and then just put some kind of metric on it that makes sense, and we're going to give the precise definition of what has to be true for the metric later. Okay, so this is the surface, and we're going to want to count closed geodesics on it. So closed geodesic, or if I just look topologically, a homotopy class of a loop. So it could be something like this, but it doesn't have to be immersed. It could, have all kinds of intersections and could be very complicated in general. But so gamma, in general, just going to call it the curve. And what I mean is either a free homotopy class of an immersion of the unit circle into a surface. But if you take a hyperbolic metric on it, this is a one-to-one correspondence to a closed geodesic, so a closed X geodesic. Yeah, and maybe I should point out that, so I said a hyperbolic surface, so I'm going to write like X is in the Teichmüller space of a surface. So it's marked hyperbolic structures that you can put on this topological surface. So basically, things, well, if I had a modelized space, it would be all hyperbolic surfaces up to isometry. Here it's up to isometries isotopic to identity. But I just want to point out that I'm not really going to talk about Teichmüller space, but there are many of them. There's R to the 6t minus 6 plus 2r dimension of different metrics you can put on the same hyperbolic surface. Okay. All right, so when I say curve, I either mean free homotopy class of an immersion, so just a loop can intersect many times in general, or if I have fixed a hyperbolic metric on it, I take it's the same as a closed geodesic. So it's a fact from hyperbolic geometry that within each homotopy class, there's a unique geodesic. And we can think of it as pulling tight. So a geodesic is the shortest length in its homotopy class. So if I take continuous deformations on these loops, and I just take the shortest possible one with respect to a metric I have on it, that's the corresponding closed geodesic. So it's unique as long as I have negative curvature. Okay. Slightly more general, we're going to talk about multicurves. So a multicurve is a formal linear combination of curves. So where each gamma I is a curve such that they're distinct. So I already defined it up to homotopy. So they're distinct curves. So they're non-parallel. So if I take the geodesic representative, they're really distinct geodesic. And the AI are some weights. And we're going to take the AIs to be in integers, or let's say in Q. It would work also if you just assign real numbers. There's some things later that makes it a bit easier if they're rational. Yeah, it's just a formal sum. So it's just, yeah, for example, here, if this is alpha and this is beta, maybe 2 alpha plus 1/3 beta is a multicurve. So it's really like the union of these curves with some weights. Okay. Let's see what else we need. Yeah, and so we're going to count. So there's infinitely many curves, infinitely many closed geodesics on any surface. But if we restrict the length, so let me define the length of a curve. So if it's a length of a free homotopy class of a curve, it's going to be, well, with respect to a metric. So maybe I say length gamma is, so L sub x of gamma is just the length of a geodesic representative. And for a multicurve, we just do it the corresponding weighted sum. So it's just the sum, the weighted sum of the individual curves. Okay. Sorry? Yeah, so basically when I say a curve, I mean either, like if I don't have a metric, I mean the whole free homotopy class. But when I talk about the length, I need to have a metric, and then I take the geodesic, so the shortest length in this homotopy class. Any other questions? All right, so counting. So given a hyperbolic structure on our surface, if we look at the number of curves close to geodesics whose length is bounded by some fixed L. This is always finite. So maybe just a quick picture. If I have any geodesic, any geodesic on here, and here's maybe another one, first off, I can homotope them to all be loop space at some point. If I fix some point on my surface, and I can just drag each one of these to start and end at that thing. Right, so I can get an I can get an upper bound on how many there are by counting loops based somewhere. And any loop, if I look at, maybe I call it gamma sub p, so a loop based at p, well, if I lift everything to the universal cover, if I lift p to some p tilde, then any loop based at there is a path, so a geodesic path, if I take a geodesic representative, to some gamma of p tilde for gamma in the fundamental group or in that discrete group gamma. Right, so every loop based at p corresponds to, if that loop has length at most L, then this has length at most L. And if we want to think about the fundamental domains, there's exactly one translate in each fundamental domain. So for each fundamental domain, we get exactly one loop based at p. And if I now restrict the length of them, so if I restrict the length of these, I also restrict the number of fundamental domains that are there. So that's why it should be finite. Sorry, I'm going to do a lot of proofs by pictures, so please ask me for questions if you have any. But if we don't restrict the length, there's infinitely many, which can be seen also by this picture by just taking them longer. But I think a nicer way to see it, because it's also how we will sometimes think about them, take any closed geodesic you want. I take this one. And take any simple curve that intersects it. So maybe this one. Then I can, instead of going like this, I can change my purple curve by cutting it where it hits this, and instead of crossing it, it follows it around. And I can do this as many times as I want, and then at some point continue on with this. Right? And I can do that, so even based on just this one curve, I can get infinitely many new curves by just doing this. So this is known as a Dane twist, right? And I can do this many times as I want, but notice, of course, the curve gets longer and longer the more I do this. So in particular, and something we'll get to soon, the new curves that I create have the same number of self-intersections. And in fact, by definition, they lie in the same mapping class group orbit, because a Dane twist is a mapping class. So even, there are not just infinitely many closed geodesics in general, there's infinitely many, for example, simple closed geodesics. If I had done this to something that was simple already, it would continue being simple. Or there's infinitely many closed geodesics of any given self-intersection number. And yeah, so it's finite, but goes to infinity as L goes to infinity. So when we say counting, what we want to say is at what rate does this go to infinity? So let me say one last thing that is still from what I said on Friday, for those of you that were there, but then we will diverge a bit. So Huber proved, I should maybe say also Hayhall. So at least Huber's was in 59, and Hayhall a bit later. That if you put no restriction and just count all closed geodesics, so X is a hyperbolic surface, and whose length is bounded by L, these grow asymptotically like e to L over L. So Huber proved this for closed surfaces, Hayhall for allowing punctures. Yeah, actually, sorry, I should have said this. I think maybe I said it, but I didn't write it. If I have punctures, my hyperbolic structure will always be complete on finite area. I will mostly talk about closed surfaces, so that wouldn't matter. But if we have punctures, like you said, like Martin said, we want them to be cusps, not funnels. So it has to have finite area. Okay. So, but anyways, this is asymptotic, meaning that the limit as L goes to infinity of the ratio of this is 1. But what we're going to talk about instead is to put some restrictions on our gammas for particular, for example, say that it's not allowed to self-intersect for simple ones. Or more generally, so the question is it's going to be, so what if we restrict to fixed topological type? So by that, I'm going to need a mapping class group. So this is my very non-standard notation for a mapping class group, but I can't change it. I get confused. So it's just the orientation preserving homeomorphisms of your surface up to homotopy. Or if you want, orientation preserving diffeomorphisms up to isotopy. Okay? And we say the two curves are the same topological type. Or just same type, if they lie in the same orbit. So if they differ by mapping class, if they differ by homeomorphism, up to homotopy. Okay, so just to get some sense of what this is, first off, these preserve the self-intersection number. So for example, if you take closed geodesics that are simple, so no self-intersection, then and you apply a mapping class to it, it's still going to be simple and true for any, say, k self-intersections. Let me first just define what I mean by self-intersection. So it's a geometric, so not signed. So if we have two curves, so let me first define it for two. Maybe I should define it for intersection first, and then I do self-intersection. Geometric intersection number. So say alpha, beta distinct curves, which again I really mean free homotopy classes of curves. Then the intersection, which I'm going to denote by I alpha beta, is the minimum number of transverse intersection between representatives. Such that alpha homotopic alpha, beta prime, homotopic to beta. And where all the intersections happen transversely and in general position. So meaning if I had a triple intersection point, I would want to homotopy that away to be 3 intersections. Okay. So I don't want them to be tangent. I homotopy them also. They intersect transversely. Okay, and this minimum is actually always realized by the geodesic representatives. So if you have geodesics, then you just count the ones you see. If you don't have a metric and you want to do this topological, because it really is a topological definition, has nothing to do with a metric, they are in minimal position, so meaning they achieve the smallest number of self-intersection or intersections as long as there's no bigons. Because bigons you can always move away and decrease an intersection, or monogons. So here is just no topology in here, no topology in here. Those you can always homotopy out and decrease the intersections that you see. And it turns out that this is all you need. As long as you have you draw 2 curves, not geodesics, just draw them on your surface. And as long as nothing of this happens, then the intersection number is the number you see. So you can just count. Okay. Right? And self-intersection number is then just alpha with alpha. But you have to take a little bit of care. You actually have to put a half in front of here for it to make sense. So that's why I had them distinct there. So it says alpha alpha is 1/2. Otherwise, the same definition. The half is just because, so if you have a figure 8, you want it to have 1 self-intersection, not 2. If you take 2 copies of this and try to homotopy them to minimize it, the minimum you can do is 2. Right, if I did this, it's 2. So that's the only reason why the half is there. Otherwise, it's 2. Okay, so the reason why I'm saying this, also maybe I should also say, so gamma is simple. If it's 0 self-intersection. Okay. So some facts. So we want to talk about types, topological types of curves. First off, the self-intersection is mapping class group invariant. Just follows from being homeomorphisms. And the other way, so I'm saying this because I want to talk about orbit and the mapping class group. It is not true that if you have the same number of self-intersection, you're necessarily in the same orbit, but almost, in the sense there's only finitely many orbits with fixed self-intersection number. So if I say, look at the set of gamma, such that I gamma, the self-intersection number equal to k, is a finite union of topological types. So maybe some examples. So if gamma is simple, just to get a sense of what it means to be of the same topological type, then we have a genus G surface. If I take some geodesic that doesn't disconnect my surface, if I cut along it, then what happens is, so for example, if I cut along this surface, I will get a genus 2 surface with 2 boundary components. And same thing happens if I cut here. I cut up 1 genus, but I get 2 boundary components. By the fundamental theorem of surfaces, any such surfaces are homeomorphic, right? It's just your surfaces are classified up to homeomorphism by number of boundary components and genus. So these are of same type. So we call this so non-separating simple curves are of the same type. can map one to another one by a mapping class. However, if I take something that separates the surface, so here, I now get, if I cut along this, I get two surfaces, one of genus 1 with one boundary component, one with genus 2, and 2 boundary components. If I take this simple curve, the same thing happens. So for the same reason, I can find a homeomorphism mapping one to the other one, so they're also of the same type. However, if I did something like, should I maybe have had more genus? Yeah, the only way I can partition 3 is in 1 and 2, so it was a very bad example. So can I put, if I put this, the blue ones are still, no, this split is into 2 and 3, and this splits it in 2 and 3. So the blue ones are still of the same type, but if I cut off, the color, if I did this, I cut it off into a one-hole torus and a one-hole genus 4 surface. And those are not homeomorphic, so there are different types. However, you can, by just using, there's only finitely many ways to partition these 5 genus. There's finitely many types. And this can be generalized also if you have self-intersections. You have to be a bit more careful keeping track of the self-intersection numbers. And in fact, it does grow. The number of topological types that you need as k grows will grows exponentially. There's work done about finding the asymptotic growth of that, but that's not what I'm going to talk about here. But this is just kind of to get you more of an intuitive idea what it means for them to be of the same type. Okay. Yeah.
Innocent question.
Uh-huh.
Is being of the same type the same thing as being conjugate in the...
No, so being conjugate in pi 1?
In pi 1.
No, then you actually the same geodesic up to orientation. Yeah. Yeah, so I said we have this one-to-one correspondence between free homotopy classes of curves and geodesic representatives. We also have a one-to-one correspondence to conjugacy classes in pi 1. This, okay, my geodesic are non-oriented, so I guess maybe it's conjugacy classes of cyclic subgroups of pi 1. Okay, so now at least I can state Mirzakhani's theorem. So let X be a hyperbolic surface with an underlying topological surface having genus G and R punctures. And gamma node any, and she proved this for multi-curve, but also true for, lying in the same orbit, so the action of a mapping class on a mapping class group on curves on geodesics can be generalized to multi-curve. It just acts on each component, and the weights just stay along. But for example, if you have an actual curve, so a curve is a multi-curve, but just connected with one connecting component. So, and everything of its type will also be a curve. So whether you want to count multi-curves or curves, this holds. So then the number gamma of that fixed type, whose hyperbolic length is less than L, is asymptotic to a constant times L to the 6d minus 6 plus 2r. So where C is positive. And in fact, so we're going to talk about this more at the end of the course. This can be broken. So this is going to depend on the topology. It's going to depend on the metric, and it's going to depend on the thing you count. So let me write it as there's a little c that depends on gamma node. There's a constant that depends on the topology, and then there's a constant that depends on the metric. write it like this because each one has a specific meaning that later on we can talk about. But what's important is that it depends on everything. But the growth, so it's polynomial growth instead of exponential, and it only depends on the topology of the surface, not which metric you put on it. And in fact, it also doesn't depend on the type of curve. It's going to come up in the constant, but some corollaries to this is that you could count all simple, so some constant, the constant is going to change, but it's L to the 16 minus 6 plus 2r. Or if you want all close geodesic who intersect, I don't know, less than 1,000 times, is also a constant times L to the 16 minus 6 plus 2r. And 1,000 you can change for any number you want. Again, because each one of these is a finite union of types. So if you count inside each, you just sum them up.
So, excuse me, in the first line, you found S less than something or not?
Sorry, yes. Sorry, I forgot the lengths, yeah. Okay, the length has to be there too, otherwise it's infinite, thank you. Yeah, simple hyperbolic length bounded. And here I wanted to bound the intersection and the length, sorry. And in both cases, so different constants, but L to the 60 minus 6 plus 2. Okay. So how much do I have? Okay. Yeah. Yeah, you can put anything you want. Yeah, sorry. Yeah, so less than k for all k. Yeah. It's just so this constant. This depends on k, among other things. But yeah. Okay, so let me let's see what happens if we do these things in the torus. So, so let S be the surface 1, 1, so a surface with one puncture, boundary component if you want. And let's look at simple. So we do an example with torus and simple. Yeah.
Could you respect the lines?
Oh, sorry. For the. Yeah, of course.
Yeah.
I get it. Sorry. Yeah. So let's look at the torus. And simple. I'm going to call it multi-curves. So in this case, a simple multi-curve will just be a simple curve, possibly with a weight. In general, a simple multi-curve would be where each component of the multi-curve is simple and there's no intersection between them, so that they're disjoint. But it won't come up now. So. Okay. So. So this is a hyperbolic. We put the hyperbolic metric on it. But if I put any simple closed curve here, geodesic, I can think of this as just, if I take the forgetful map, I just forget the puncture, and I look at the flat Euclidean torus. It maps to a homotopy class of a simple curve in there as well. All right, I just delete this one. So I can get a one-to-one correspondence between simple curves. So, and here, at least if I think of them as homotopy classes to simple curves. But the difference here is here we have a unique closed geodesic in each homotopy class. Here we have many parallel ones. But if we take simple curves or a Euclidean geodesic through some fixed point x, so this is not, that's a puncture. Let's look at all of the ones that pass through a specific one. So if I think of a torus as R2 mod Z2, so in other words, in R2, I have my lattice. And if I think of the origin being what projects to this point, then geodesics on the torus corresponds to straight lines in R2, right? So probably I didn't draw this very well at all. Maybe, yeah. So for every straight line, so this, I just want to say, this corresponds to straight lines, so Euclidean lines in R2. Okay, the geodesics on here corresponds to straight lines in R2. If I want them to close up on themselves, I want to get closed loops of rational slope. So to count, so if I forget the hyperbolic case now, if I just wanted to think about Euclidean closed, say closed geodesics through a fixed point, so just take one representative in each homotopy class, of length at most L, that would be the same as counting so how do you get a straight line from the origin that has a rational slope? Well, it has to hit another lattice points in here, and the length of it is this length here. So it's a number of lattice points, well, up to, we also have this side. This one is the same as over here, so I guess up to a factor of 2, it's the number of lattice points in a Euclidean ball in here. So let's see if I can finish this example, and then. So this then goes to so number of Z2, so maybe let me put the half to be, okay, intersected with balls at the origin of length L. And this we can do, this is Gauss circle problem. We know that this grows like pi L2, like the size, the number of lattice points, just integer points in R2 of normmost L. As L grows is like the radius of or the area of the ball. So we can count this. I cheated a little bit because if I took, so this was supposed to represent like 2, 3. If I did 4, 6, I would get the exact same line. And projected onto here, that would give me something that goes around this twice, which I view as a multi-curve because it's this curve times 2. So really what we're counting here is multi-curves of length at most L. So if here we wanted to count not all multi-curves but of a specific type, the type we could choose would be primitive ones that don't go over itself more than once. And it turns out that that's, well, it's not hard to convince yourself, it's exactly when these are relatively prime. So if you can count all multi-curves and you want to count a specific type, you have to know the density of these ones you want to count among all. In this case, you need to know the density of relatively prime integers among all integers, and this is known. It is pi over 6. Is that right? So if you want to count, so this is really simple multi-curves. In this case, there are no actual like multi-curves, simple multi-curves in the torus in the sense that it has more than one component, because any two simple curves will intersect on the torus. But you have multi-curves in the sense that you could have weighted. So this is really like C times gamma. So if we wanted to count like primitive ones, so actual curves, so primitive simple curves then just grows like the density. No, there's a pi, pi over 6, I think it is. It's just whatever the density of relative primes among all geodesic, it's this. Okay, so I'm doing this quickly, but it's just to get the general idea of something we're going to do in much more generality later. So I will start again with this example next time, but this is a Euclidean setting. The thing that one has to change for this setting is just you have this identification, but now you measure the length, just not the Euclidean norm, but instead for each lattice points here corresponds to a closed geodesic here, and you take the hyperbolic length of that. So you get some other constant that depends on the hyperbolic metric, but otherwise you get the L squared, which, by the way, is 6d minus 6 plus 2r in this setting. And the precise constants and so on were worked out by McShane and Riven. But essentially, this is why it works. So this was, I think, in 2001. For the precise details, but this really is the idea. And what we're going to do in general, to count this in general, it's going to be a very similar thing. We're going to replace R2 with this space of measure laminations, Z2 with simple multicurves, and the relatively prime with the things that we want to count. And we're going to see that the same kind of method works, but we have to translate everything into measures. So I'm going to start with that next time. So sorry for going a bit over time.